Today we will be studying about the duality in linear programming. So the term dual in general sense implies two or double. The concept of duality is very useful in mathematics, physics, statistics, engineering and managerial decision making. For example, in two-person game theory, one competitor's problem is the dual of the opponent's problem. In the context of linear programming, duality implies that each linear programming problem can be analyzed in two different ways, but having equivalent solution. Each linear the programming problem, both maximization and minimization, stated in its original form, has associated with another linear programming problem called dual linear programming problem, or in short you can call it as dual. Now this is unique and it is based on the same data. So in general it is immaterial which of the two problems is called primal or dual, since dual of the dual is primal. Okay, so the format of the simplex method is such that solving one type of problem is equivalent to solving the other simultaneously. Thus, if the optimal solution to one is known, that is, if you know the optimal solution to primal, the optimal solution of the other, that is, for example, it is dual, can also be read from Cj minus Zj row of the final simplex table. In some cases, considerable computing time can be reduced by solving the dual. Now we will just look how to formulate the dual LPP. Suppose the primal LPP is given in the form maximize Zx equals C1x1 plus C2x2 plus etc plus Cnxn. Okay, so this is the objective function in the primal LPP, subject to the constraints A11x1 plus A12x2 plus etc plus A1nxn less than or equal to B1, A21x1 plus A22x2 plus etc plus A2nxn less than or equal to B2, etc. AM1x1 plus AM2x2 plus etc plus AMNxn less than or equal to, here I put this etc sign over here, and BM. Here x1, x2, etc. xn all are greater than or equal to 0. Now if this is the primal LPP, what is the corresponding dual LPP and how will you define that? Now take a closer look. The dual of this problem, or dual of the primal, is written as, first we will concentrate on the objective function, minimize zy is equal to b1y1 plus b2y2 plus etc plus bm ym. Now what about the constraints? Subject to the constraints A11 y1 plus A21 y2 plus etc plus AM1 ym less than or equal to C1, A12Y1 plus A22Y2 plus etc. plus AM2YM less than or equal to C2, etc. A1NY1 plus A2NY2 plus etc. plus AMNYM less than or equal to Cn, Y1, Y2, etc. Ym greater than or equal to 0. So this is how you write the corresponding dual LPP when a primal LPP is given and if you are asked to do so. See, I know this is a bit confusing right now. As you can see, those who have closely observed can find some somewhat connection between the primal and dual of this particular LPP. Now, if you take a closer look on the objective function, you can see that the maximization problem has converted into a minimization problem when it came to the dual. Also, regarding the right hand side of the constraints, if you take a closer look, b1, b2, b etc. bm in the in the right hand side of the constraint of the primal, okay, is now appearing as the coefficient of the objective function, coefficient of the variables in the objective function. That is, it is appeared as the coefficient of y1, y2, etc. ym, and that too in the objective function. Okay, now what about the variables in the constraint x1, x2, etc. xn? It have changed into y1, y2, etc. yn. Okay, then what else? Okay, so these are the some of the changes that you can observe. Now let's see. I'm going to give a general LPP model from this. So I'm going to write the general LPP model, and in the case of primal you can write it as maximize zx is equal to summation j is equal to 1 to n cj xj, okay, subject to the constraints, subject to the constraints, summation aij xj less than or equal to bi, where I takes the values 1, 2, 3, etc. up to m, j is equal to 1 to n over here. Okay, xj is greater than or equal to 0, where j takes the values 1, 2, 3, etc. up to n. What about the dual? Minimize zy is equal to summation I is equal to 1 to m biyi, subject to the constraints, subject to the constraints, summation aji yi less than or equal to cj, I is equal to 1 to m, j is equal to 1 to etc. n, yi greater than or equal to 0, I is equal to 1 to etc. up to m. So this is a general LPP model, whatever I have written over here and the previous in the formulation of dual LPP, that I have consolidated. Okay, now let's see the relationship between the primal and dual. Now, if in primal, if the objective is to maximize, okay, if the objective is to maximize, then in the dual the objective is to minimize. Fine. Now if the variable, if in primal the variable is xj, here in the dual the constraint is j. Now here if the constraint is I, then here the variable is yi. Then the variable xj is having an unrestricted, is unrestricted. If it is unrestricted in sign, then constraint j, in the case of dual, constraint j will be of the type is equal to type. Okay, now see, all these things you will be a bit confused right now. Now after explaining the relationship, what I'm going to do is I'm going to give you 2-3 problems, and after that you connect all these things. After doing the problem, you connect the theory part of the problem and you will get a better idea. Okay, now if in primal the constraint I is of equal to type, okay, if it is not greater than or equal to, okay, then in the dual the variable yi is unrestricted. Okay, now you can closely observe that everything is just opposite. And whatever is happening in the primal, it is in dual, when it comes to dual, it's just the opposite. Now in 6, less than or equal to type of constraint. If you have a less than or equal to type of constraint in the primal, then in the dual, okay, in the dual it will be greater than or equal to type of constraint. Okay, one more, the last one. If xj is unrestricted in sign, then jth constraint is an equation. Okay, so just take a pause and just read this relationship. We'll move on to a problem right now. So the first problem, right, you can do the problem along with me. Write the dual to the following LPP. Now your problem is a maximization problem. Maximize z is equal to x1 minus x2 plus 3x3 subject to the constraints x1 plus x2 plus x3 less than or equal to 10, 2x1 minus 0x2 minus x3 less than or equal to 2, 2x1 minus 2x2 minus 3x3 less than or equal to 6, x1, x2, x3 greater than or equal to 0. Now the solution. So in this particular LP problem, there are what are the number of constraints? Constraints is equal to 3. That is, I'm denoting it by M. And how many variables are there? Variables, that is also 3, and I'm denoting it by N. Thus there must be, so in the dual there must be how many variables must be there? Yes, there should be M equal to 3 variables and N equal to 3 constraints. So this thing you should be clear. Further, now regarding the constraints and the variables, we are clear right now. Further, what we are a bit confused about is the coefficients. Okay, now here the coefficients in the case of a primal variable, coefficients in the case of primal variables, that is c1 is equal to 1 comma in the objective function. Okay, c2 is equal to minus 1, and what about c3? c3 is equal to 3. Now these are the coefficients in the objective function, that is the objective function of what? Of the primal LPP. So the primal variables are given in the form of c1, c2, etc., c3. Now this thing, when it comes to the dual part, becomes the right hand side constraints, right hand side of the constraints of dual, right hand side of the constraints of the dual LPP. Now I will show you how this happens. The right hand side constraints, now in the primal, the right hand side constraints, the right hand side of the constraints, okay, of the constraints in the primal is given as what? b1 is equal to 10, b1 equal to 10, b2 is equal to what? 2, and b3 is equal to 6. Right, so this becomes the coefficient in the, now this becomes the coefficient in the dual problem, dual objective function, in the dual objective function. Okay, so or the dual problem, the objective function in the dual problem. Now finally we'll say that the maximization, what we have over here is maximization. So we say that the problem should be of a minimization type, and let's see what we will get. So minimize zy is equal to, I have said that the right hand side of the constraints is going to be the coefficients of the objective function. So what will I get? 10x1 plus 2x2 plus 6x3. Sorry, these are all y. Should take care of this. Okay, that's my mistake, so you should take really care while converting. So zy is equal to 10y1 plus 2y2 plus 6y3 subject to the constraints, subject to the constraints, y1 plus 2y2 plus 2y3 greater than or equal to 1. So from where did I get this? Just go back. Yes, you have 3 constraints over here. Now what I'm going to do is just mark this as red. Okay, I'm going to take this vertically, and this thing will be written as my first constraint, right? So instead of x1 it will be y1 plus 2y2 plus 2y3. Fine. Now just see the inequality, it is less than or equal to over here, so I made it as a greater than or equal to sign. I'm finding out the dual. Now where did I get this one from? Yes, it is from the objective function, this one. Okay, so any guesses about the second constraint? Okay, let's move back. Now what is the second constraint? Something that has to be done with this. Okay, so let's see what our second constraint is. y1 minus 0 y2 minus 2y3. Now what about the sign? Yeah, greater than or equal to. What about the objective function? Minus 1. So it's minus 1. What about the third? Third is concerned with this. So how will you write that? y1 minus y2 minus 3y3 greater than or equal to 3. From where did you get this 3? From the objective function. y1, y2, y3 greater than or equal to 0. Hence, the first problem is solved. Second problem. Okay, so the next problem is obtain the dual problem for the following LPP. You have to minimize z is equal to x1 plus 2x2 subject to the constraints 2x1 plus 4x2 less than or equal to 160, x1 minus x2 is equal to 30, x1 greater than or equal to 10. So here you have to transform all the less than or equal to type constraint to greater than or equal to type. Okay, now how will you convert that? Since this is a minimization problem, this should be done first. So that is our first step. So how will you do that? Now we have the first constraint like this, 2x1 plus 4x2 less than or equal to 160. Just multiply this by multiply the first constraint by minus 1. So what will you get? 2x1 minus 2x1 minus 4x2 is greater than or equal to minus 160. Fine. Now what about this? Now you have an equal to, also you have the equal to sign over here. So this constraint should be split into two parts, greater than or equal to and less than or equal to type. So first of all, what you have to do is one, whenever you get an inequality like this, x1 minus x2 greater than or equal to 30, x1 minus x2 less than or equal to 30, you should write like this, split it into two, and then you check whether this is a minimization problem. So if it is a minimization problem, this constraint, when you split it into two, this one you can write it like that itself, that is x1 minus x2 greater than or equal to 30. What about this? This should be again multiplied by minus 1 in order to make it as greater than or equal. So minus x1 plus x2 greater than or equal to minus 30. So that is your another constraint. Then you have x1 greater than or equal to 10. That you can write it like that itself. And then you have what? then you have the variables x1, x2, x3 greater than or equal to 0. Now it is ready for the ready for converting into a dual problem. So let's see. Let y1, y2, y3 and y4 be the dual variables. Be the dual variables. Okay, corresponding to the four constraints. Right, so let's see how I will turn this into a dual problem. You can maximize this since this is a minimization problem. Z pi is equal to, now here here you have, now you don't have to look at this, just look at this constraints. Now you have minus 160, 30 and minus 30 in the right hand side. So what happens here in the objective function? Yes, minus 160 x by 1 plus 30 by 2 minus 30 by 3 plus 10 by 4. This is your objective function subject to the constraints, minus 2y1. So what I have done over here, yeah, I have taken this into consideration, right, first. So minus 2y1 plus y2 minus y3 plus y4 is less than or equal to 1, right? Oh, sorry, I should take this one also. This is also a part of the first constraint. What about the second constraint? Second constraint, you can write it as similarly minus 4y1 minus y2 plus y3 less than or equal to 2. So there are only two constraints right now, y1, y2, y3 and y4 is greater than or equal to 0. Okay, so this is what you are getting right now.